Before you start watching, I should warn you that it may be hard to grasp some moments straight away, so I invite you to pause and ponder anytime you feel you need it. There are also text fragments in the following steps that provide the same content as the video. You may read through them instead of watching the videos if you find that format preferable. Let's look at what happens if we try to print out the result of map function without turning it into a list. Well, nothing really special. It just lets us know that the object we're working with is not a list but a map object. I've mentioned earlier that such objects are still iterable. In Python, in order for an object to be iterable, it just should support the so-called iterator protocol. An iterator is a special kind of object that supports few characteristic functions. An object is iterable if we can receive an iterator out of it by using the iter function. In particular, when you apply the iter function to an iterator, you get this iterator as a result, so iterator objects are iterable as well. As you may have guessed, map, filter, and other objects mentioned in the lesson on list processing functions are in fact iterators. It's safe to think of an iterator as of a sequence of objects that support few key functions. One such function is the next function. The next function returns the current element in the iterator and moves iterator to the next element of the sequence it contains. Let me explain. Iterator is kind of a sequence we can move through by using this next function, but can't move back. That means that once we've applied the next function to an iterator, it now contains less elements. For example, if we turn iterator into a list after using the next function for several times, the resulting list will be shorter than if we didn't apply the next function. Once we reach the end of the iterator by using the next function as many times as there are elements in the iterator, an attempt to call the next function once again will cause the stop iteration into exception. Let's exhaust this iterator that is a map object and see what happens if we turn it into a list. One other thing to know is that functions like list called on an iterator exhaust it, that is, go through all of its elements. That's because such functions iterate over the object they are given. If you iterate over some iterable that is not an iterator itself, that's what actually happens. An iterator of this iterable is created by using the iter functions and then it is processed. But if you iterate over an iterator, there's no copy created and you actually go through all of its elements, thus exhausting it. So don't try to use iterators after calling list on them. That will cause the stop iteration exception, no matter how much elements there were left before the call. To understand better what happens, we can create our own custom iterator. To do this, we need to define a generator function. A generator function is basically a function that uses this yield statement. It's called so because it generates the elements of the iterator one by one. So iterator is the result of work of the generator function. Thus, seq is an iterator. Insec is a generator function. You see, this yield statement is kind of like return statement, except it doesn't terminate the function's work, but it suspends it for a while, until the next function call is performed. Then the function proceeds to run from the place it's been suspended at. For example, this insec function is the same as calling iter on the result of range function with one argument. It yields 0, then 1, then 2, and so on until we reach n-1, which is the last element of the iterator generated by insec. As you may see, when we iterate over it, the iteration starts from 1, since we've already moved from 0 by calling next previously. And trying to call next after we've iterated over an iterator causes an exception to occur, as does an attempt to call next after implicitly iterating over the iterator by calling the list function. Let's look at another implementation of this generator function. It simulates the behavior of the previous generator by manually raising the stop iteration exception when needed. We may use return statement within the body of a generator function as well. It makes kind of the same thing as raising stop iteration. Once the execution of the generator reached the return statement, it means there are no elements for iterator to yield anymore, so calling next once more is a bad idea. It is kind of safe to think that return and stop iteration make the same thing within the context of designing a generator function, but they clearly don't. Consider this example. Since we raise an exception, it is called by the try except construction, and our generator function has two values to yield. If we write return instead, there is no exception to catch, and the generated iterator is exhausted after yielding a single value. Here's an example of how these subtleties may show up. Suppose we have a list of numbers, and we want to compute the average of their squares. Well, the squares part is easy. Now, we may want to write a function that computes the result like that. But squares returns an iterator, and while sum does work with iterators, len doesn't. So we need to write our own length function that would work with iterators, or transform the result of squares into a list, but there are reasons why we don't want to do that. We could map over an iterator to make every element to be 1, and then count the sum of the resulting sequence. Or we could write it like it's written below. So let's check it out. Well, we get zero division exception. That may be unexpected for some of you. Okay, so what's the problem? Well, the only place where division occurs is within the body of average function. Thus, our length function returns 0 for some reason. But on its own, it returns the result we expect. But now the problem becomes obvious. We use two functions that both pass through the iterator that average functions is given. So there are two possible solutions. First, we may somehow create two identical but separate iterators, one to pass to sum and one to pass to length. But it's much better to simply pass through iterator once, keeping track of two values instead of doing it twice for each value. We may have a tuple with sum as the first element and the length as the second element, and modify each of these values as we pass through the iterator, like that. Then we can define average like that. Okay, so it's kind of under the hood implementation of iterations in Python. For some reason, it is perhaps more convenient to construct this weird iterator object in order to iterate over a list. But why do we need to return these weird objects from functions like map, filter, accumulate chain, and so on? After all, some of them return lists in Python too. And why do we need to get into this weird implementation details anyway? The thing is, it is the way to make our computations lazy in Python. You see, the generator functions, they generate the values as they go, on demand. They don't actually allocate space for the entire sequence of elements they are yielding. That enables us to make our computations more efficient and do some really neat things. Consider these function numbers. You don't see any terminating conditions for a loop within the function's body because we don't need any. This function generates the sequence of all the non-negative integers. But since iterators are lazy, they don't try to compute the entire sequence they contain. They don't need to. They will generate a result and yield it to us if we need to, on the fly. Like that. And the fact that map, filter, and all these functions return as iterators and not lists enable us to operate on infinite sequences without losing the property of laziness. For example, this way we may get the sequence of all the squares of all the non-negative integers. And this construction here is called a generator comprehension. It's like list comprehension, except it returns an iterator, thus the result is lazy. By the way, you may omit the braces if you pass a comprehended iterator to some function as the only argument. Now, let's look at some more functions from the iterators model to work with iterables and iterators in particular to keep things lazy. T creates two independent copies of some iterator. Independent means that iterating over one of them doesn't change the other. If you want to create more copies, then you may specify the number you need as an optional parameter for the T function. This is a useful thing, because using one iterator in different processes is a really bad idea. Count is simply a generator equal to our numbers generator. That is, it returns an iterator containing the infinite sequence of integers starting from 0. It has two optional parameters, the starting point and the ending point of counting. Cycle takes an iterable and returns an iterator that repeats the elements of the iterable infinitely, like this. Repeat takes one element and returns a generator that repeats this element infinitely. It's like a cycle for one element only. iSlice is a lazy version of list slicing. It works pretty much the same except it's a function, it works on any iterable, and it returns an iterator. You have to specify the iterable you're taking slice from. If you specify one additional optional parameter, it is considered to be the ending point of the slice. If there are two parameters, they are considered as the starting point and the ending point, in that order. If you want to specify only the start, you may give none as the ending point. Finally, if you pass 3 additional parameters, the third one is considered to be a step. Negative steps are forbidden, unlike the actual list slices. Let's look at two other quite important features of generator functions. First is that the yield expressions may be used to transfer information both sides. Instead of getting a value from the generator, we may send a value to it. Look at this counter. It's basically the same as our numbers function defined earlier, except now we don't only have the name of the value we want to yield on the right of the yield keyword, there's also an assignment statement on the left. That means that we can use a special method send to set the value of the thing on the left of the yield keyword to some value. For example, we may want to set the counter to be 0 again. Notice that when we send something, the yield statement doesn't only set the value of new to that something, but it also yields this something as the current result of the generator function. Also notice that if we use next without sending any value, then new is automatically set to none, which is why this works without us setting new to none or 0 explicitly in the if branch. That is cool, but it is not really a functional programming-like thing to do. There's an even greater thing, the yield from construct. Consider this limited counter generator function. I hope it is clear what it does. Let's now create two separate iterators by applying the generator functions to some arguments. Now, let's make a new generator function that's running the first such iterator, then once it's exhausted, it runs the second iterator. That is exactly what yield from enables us to do. It's not just a construction for iterating over some iterator. We're actually switching to the iterator we're yielding from. That is, we may set value to it and so on. It's like we delegate the yielding of values to this iterator. Look at this double lim counter function. Now that we know how to preserve laziness of the things we're processing, let's define some very common functions from the functional programming toolbox. First, these drop and take functions are quite common to use, and it makes sense to use them instead of writing islice explicitly each time we need them. Also, hand and tail are used a lot, and now we want to make them lazy to work directly with iterators. Sometimes we'd like to force the computation. This is an absolute synonym of taking some lazy slice and applying a list constructor to it. But it's kind of nice to have this function as one, and also to have a name that reminds us that what we're actually doing is forcing the computation, because it may cost a lot of resources. There is also this very useful function called iterate. Iterate takes a function and some element x and returns an infinite sequence where the first element is x, the second is f of x, the third is f of x, and so on. A possible implementation may be this one. But there's a recursive call, and hence we're limited to about 1,000 of elements. So it's more preferable to avoid using recursion because iterate is frequently used to generate large sequences. Here's another implementation. Here we generate an infinite sequence of x's first, and then we're going through it with accumulate. But instead of making something with two consequent elements, we're simply ignoring the second argument and defining the current element of the sequence to be f applied to the first argument of the accumulate, which is the previous argument of the sequence. Please consider revising the lesson on list processing functions if you don't fully understand how it works. There are less trivial applications, of course, but here's one to demonstrate an example of how iterate works. Let's look at the second implementation of numbers generator function. It is essentially the same since it returns a sequence starting with 0, then the result of applying inc to 0, which is 1, then the result of applying inc to the result of applying inc to 0, which is inc of 1, which is 2. By the way, we could generate church numerals in the same fashion by using the 0 function as the initial value and the successor function as an iterative function. And here is another example of using these tools. You're probably familiar with this technique of systematically generating prime numbers by going through the given sequence of numbers, defining the first number of the sequence as a prime number, then filtering out all the numbers ahead of it that are divisible by it, thus making a sieved sequence, and then applying the same procedure to the sieved sequence. It is called the sieve of Eratosthenes. Here's exactly the recursive algorithm expressed as a generator function. Except we can make use of the fact that our computation is lazy, and thus pass the function the infinite sequence of integers beginning with 2. The result is an iterator containing an infinite sequence of prime numbers. Of course, we can generate all the prime numbers using this method, at least because of a limit for a number of nested recursive calls in Python, or due to fundamentally finite amount of memory. And still it works quite well. If you struggle to understand any part of this generator function, please review the part of this lesson about yield and yield from statements. We can use similar technique to implement a canonical Haskell version of Fibonacci number sequence generator. We make use of the fact that if we write down a sequence of fibs, and below the fib sequence we write the same sequence starting from the second element, then summing the corresponding elements of these sequences will give us the original fib sequence starting from the third element. Below is a rough visual representation of what's going on. The idea is that by summing the first element of fibs 1 and the first element of fibs 2, which is the second element of fibs 1, we get by definition the third element of fibs 1, which is also the second element of fibs 2. This element is appended to the general fibs sequence, so it is the next Fibonacci number, and hence it is appended at the end of both fibs 1 and fibs 2. But since we've summed the first element of the fibs 1 and fibs 2, we used next on each of these sequences once, and each of them shifted one element further. Thus, we may repeat this process again, sum the new first elements of these sequences to get the next value for both fibs 1, fibs 2, and simultaneously move both fibs 1 and fibs 2 to the next element. This may only work if our computation is lazy, and deepen doesn't require a complete finite sequence, but may operate on structures that build themselves while they are used. In this picture here, red color represents that in this step these elements are already nexted, if you will. There's another kind of tasks we may apply these techniques to. There's a common pattern among computational problem-solving approaches called incremental improvement. The idea is that we're trying to approximate the solution by iteratively improving our estimate. We say that we improve an approximation until convergence. Convergence most often means that our two consequent estimations are close enough. This close enough is defined in different terms. When the answer is numerical, it usually means that the absolute difference between two approximations is less than some small predefined value. Let's look at a simple example. You might be familiar with the notion of series expansion. A series expansion is a representation of a function as an infinite sum where terms depend on this function's arguments. The sum converges to the value of the function on that arguments. Series expansions are great tools for computing approximate values of some functions. We may count the sum up to some term to have an answer with precision that depends on the number of terms. We don't need infinite precision, of course, so we define a threshold and start computing new terms, adding them to the result. If at some step our approximation altered less than the value of our threshold is, we assume that the answer is precise enough. For example, this is a series expansion for e to the x value. Let's implement a generator that returns a sequence of approximations of this function, ending with the one satisfying the convergence condition. It's done quite simple. As you can see, it works quite well, pretty fast, and it offers us the entire sequence in case we want to observe the approach to the result. This particular procedure may be generalized to fit a lot of other similar computational problems.